The Canadian Institute for Advanced Research brings together top researchers around the world to work in global networks whose focus is to answer big questions of importance to the world. So quantum materials are the frontier of material science. Materials are at the basis of our technological world, and we're interested in exploring the new and exotic properties at that frontier. For example, quantum materials might be a good example is superconductors. A superconductor can transmit electricity perfectly, zero resistance, no loss of energy at all. It's perpetual motion, almost a magical property. You can flow a current, a lot of current, in a small wire that is superconducting and, for example, transmit electricity over great distances. Superconductivity is already used today mainly to make powerful electromagnets that are used in magnetic resonance imaging. But if we could make superconductors work at room temperature, then we'd have a major technological revolution. In the quantum materials program, our mission is to understand how electrons behave, how they work in certain materials. To do that, we have three different kinds of experts. We have theorists like Steve Kivelson at Stanford. We have materials experts like the group of Doug BONN at the University of British Columbia in Vancouver, who make materials, synthesize the actual materials. And we have experimentalists. In 2007, we made a great discovery. We got samples from UBC, the group we'd been working with for 20 years, and performed measurements in Toulouse. Toulouse is one of the few 3 or 4 labs around the world that can produce the very large magnetic fields that we need. The big surprise was that we saw something called quantum oscillations. Observing those quantum oscillations was like the tip of an iceberg. It showed us that we were not thinking in the right way about how electrons behave. And so now the field has really been transformed by that discovery.
What was so surprising about it was that people expected that in that range of the phase diagram, if you suppressed superconductivity, the material would be more or less insulating. The appearance of quantum oscillations is a sure sign that they're actually metals, not insulators. Our role in that was that to see quantum oscillations requires ultra-high purity crystals. And that came together with very high magnetic field measurements and then Louis Taillefer's group's expertise in quantum oscillations in other materials at Sherbrooke.
The role of a theorist like Steve Kivelson has been to guide us into where to look. The theorists are very effective in providing us guides, ideas, making predictions that we can test as experimentalists.
One of the key questions that many people addressed was, how does the system evolve as a function of doping from the undoped antiferromagnetic insulating state to the non-magnetic high-temperature superconducting phase?
The copper oxides that we study can be doped, so-called, which means that we can tune the density of electrons moving around in the material by adding or removing oxygen. And the fascinating thing is that the superconductivity, the most robust superconductivity we know, occurs between the insulator and the metal in this intermediate region. The discovery led us pretty quickly to a new discovery, fundamental one, that in addition to superconductivity as the main property of these materials, there's another property, another phase of electronic matter sort of competing with it. And that's the key now to understanding how these materials function.
One of the key positive features of the CIFAR program in quantum materials is that the students have their own network within that quantum materials program. They run their own workshops, and they're actually highly mobile within the network.
So there are postdocs coming in from other labs, other program members sometimes, that are very motivated by what they do and transfer this motivation to us. So we have access to a variety of experts right here in the lab. So some people that I work with every day have made fantastic discoveries, and I get to be a part of this because they're here.
CIFAR has played a key role and bringing together these different experts from around the world to focus in a sustained way on answering these big questions that have the potential to transform our world.